Greetings everyone, my name is Nikos Charalampidis and today I'm going to present to you a chaotification model based on Modulo operator and Secant functions for enhancing chaos. First I'm going to start with an introduction and then I'm going to present to you the chaotification model and how this is applied to existing chaotic maps. Then I'm going to show you the application of the new maps to the problem of pseudo-random bit generator. And lastly, I'm going to conclude this presentation with some conclusions and future extensions. As I'm very well aware, you've heard many times till now what is chaos. So I'm going to start my presentation by telling you that there are two major areas for chaotic systems. The first, it is chaos emergence in nature, with examples in engineering, meteorology, biology, astronomy, and basically in almost all physical phenomena. The second is chaos applications, with examples in robotics, weather forecast, pandemic crisis management, circuits, information security. In particular, in the discipline of information security, there are many advancements in the field of chaos-based cryptography, with a wide spectrum in applications. For example, in random bit generators, watermarking, hazing, secure communications. The determinism, the dubious behavior, the low computational cost, and the simple structure of chaotic systems provide an excellent foundation for implementing a plethora of encryption schemes. However, in many maps, for example, the logistic map and the sign map can exhibit periodic behavior. Thus, not all parameter pairs are admitted for encryption. This means that these maps are vulnerable in attacks, for example, through initial state identification and parameter estimation. Therefore, there is a clear need for maps that exhibit a wide parameter range of uninterrupted chaotic behavior. So, motivated by this, we designed a new chaotification model, as you can see in equation 1, in order to improve the complexity of existing chaotic maps, based on Modulo operator and Secant functions. Its structure is comprised of two parts. The first part is the Secant function, which has an immediate influence on the output of the sigma, becoming thusly a source of chaos. And the second part is the Modulo operator, which limits the output range. Now we take our chaotification model and we apply it to different existing chaotic maps, with the first one to be the logistic map. As you can see immediately from these figures, while on the right figure we have the original logistic map as you can see for a wide range between 0 and 4, this map exhibits periodic behavior. On the modified version, in almost all range from 0 to 4 exhibits chaotic behavior. And this is being verified by the corresponding Lyapunov exponent diagram, where you can see in the red we have the Lyapunov exponent diagram of the original logistic map, and in the black we have the Lyapunov exponent diagram of the modified logistic map. And interestingly, as you can see, we have also high values of Lyapunov exponents. In the second map, we take the sign map, and again, in the original sign map, there are regions where we have periodic behavior, while in our modified versions, we have in the entire spectrum of 0 to 10 only chaos, and this is also being verified through the corresponding Lyapunov exponent diagram. In the third map, we take the sign map, and again, while on the right there exist regions with periodic behavior, on our modified version we have only chaos, and this again is verified by the Lyapunov exponent diagram. The last map we are going to present to you is the modified cosine logistic map. While again on the original there exist regions where the map exhibits periodic behavior, our new modified version of the cosine logistic map exhibits only chaotic behavior. Now, to investigate further our systems, we apply them to the problem of random bit generator. So, firstly, we take a random bit generator, which first we take a PI, which is given by this rule, and QI, which is given by this rule, and we produce the P bits and the Q bits, and then we combine them through an XOR operation to finally take our resulting bit stream. By applying this pseudorandom bit generator to our chaotic maps, we then need to assess the randomness of this suggested technique on a set of 100 million bits using the National Institute of Standards and Technology Federal Information Processing Standards, or commonly the NIST tests. And as you can see, in all new chaotic maps, the modified logistic map, the modified sign map, as well the modified sign map and the modified cosine logistic map, the generator passes all tests, which basically means that our chaotic maps are good to be used for encryption-related schemes. To conclude my presentation, I have presented you a chaotification technique for one-dimensional chaotic maps, which can be used to improve the complexity of a sigma. The technique was assessed on a set of maps, resulting in increasingly chaotic behavior, as demonstrated by the bifurcation and Lyapunov exponent diagrams, as well as by a pseudorandom bit generator application which was tested and passed all these tests. The new maps have a larger key space as a result of the addition of 3 control parameters, and finally, it can be concluded that all of the above characteristics can lead to robust chaos encryption applications. For future extensions of this work, we'll include full analysis on the modified maps with Lyapunov exponent diagrams with respect to 2 parameters, phase diagrams, and research of fixed points. In addition, a modification to this existing chaotification technique will be researched in a way that the modified maps will showcase improved statistical randomness in comparison with the seed maps, and furthermore, comparison of the proposed technique with other chaotification techniques will be included. Lastly, this work will be generalized to 2-dimensional maps. Thank you.